Today we're going to talk about Lesson 8, Combinations. This is one of the more challenging lessons in the whole semester, possibly the hardest, but there's a lot of stuff going on, so we're going to break this into a few different videos here. We're going to start off with the introduction and the definition stuff and a few examples, and then we're going to get into some slightly different classes of examples in later videos. So we talked about permutations in lesson 7, right? That was the number of ways to select R things from a set of N things and order them. Combinations is the same concept with order removed, right? How many ways can you select R things from a set of N things without repetition Oh, and where order is not important. That's what we're going to be looking at, right? So it's combinations of things, it's groups of things rather than an ordering of things. We don't have a specific definition that jumps out at you like permutation as an ordering. We're just going to be looking at this, right? So that's what we're looking at. I think I'm going to do an example and then I'll give you the formula, right? So, for example, how many ways, how many sets of 3 letters chosen from A, B, C, D, E, excuse me, where order is not important. Well, we've got A, B, C, we've got A, B, D, that's a B. We have A, B, E. Let's see, A, B, C, A, B, D, A, B, E, right? We have A, C, D. We have A, C, E. And we have A, D, E. I believe that's all of them with an A in it. All the different combinations, B, C, D, E, okay? So now we'll move to B. B, C, D, right? B, C, E. B, D, E. I believe that's all of them. This is a B. My B's are always a challenge. That's a D. And then finally, C, D, E. There's 10 different ones that have 3 letters with no repetition, chosen from that set of 5. So let's get that also from the formula. If you want to, I spend a lot of time when I teach statistics doing these. This is essentially a sample space right here, right? You want to select 3 things from a set of 5 things. How many different ways can you do that? Well, our combination formula will tell us that there's 10 different ways to do that. But you can actually list them, and in statistics we actually do list them. If this was a sample space question, you would actually want to list those because that's the sample space. And it's nice that there's some overlap there. And one of the things that gets reintroduced in lesson 8 and 8.5 is we come back and do some more probability again. So that's important, right? So the number of ways to choose, I guess I don't need these, I don't want this room, are things from a set of n things where order is unimportant. Is C of n comma r, which is the notation your book uses. Another notation for that is NCR. This is the notation you'll find in your calculators. And once again, just like with permutations, I strongly encourage you to find that button on your calculator, right? And that's just going to be n factorial divided by n minus r factorial. That's a minus sign, times r factorial. You're dividing out the number of ways to arrange those. I think I'm going to rewrite that to make that clear. That's a minus sign, n minus r factorial. So it's pretty much the permutation formula with that little r factorial added in, and that shrinks down the number of number of the ways to do this, because order is no longer important, and that's actually, they're going to end up being far smaller numbers because of that. Okay. Once again, if you're using this formula, then you're doing it the hard way. You really want to figure out how to do that on your calculator. So the first one I think I want to do is the example 5 from the book. A poker hand has 5 cards. How many poker hands are possible? And so C of 52 comma 5, or 52 C5. Now, if you weren't thinking about it a lot, you might say, but wait a minute, order is important in poker. You know, you have straights, you know, 7, 8, 8, 7, 5, 8, 7, 6, 5, 4, right? Things like that, where order is important. But the order that they come into your hand is not important, right? So it doesn't really matter, except in straight poker, it's more important because people are looking at when they're coming into your hand. But in general, if you're looking for the highest hand, it doesn't matter what order they came, and you're just getting the highest hand, right? So that number is, well, let's crack the calculator. 52 NCR 5. 2598960. Right? About 2.6 million different poker hands are possible. Doesn't actually seem like a lot to me, but that's all there are, right? And you're including all the different options. Every card is treated differently in that case. So, you know, the ace of diamonds and the ace of clubs, and 3 small ones is different from the ace of hearts and the ace of spades, and the same 3 small ones, etc., etc., etc. Okay. Let's do this example. So let's suppose we had I'm just gonna choose one, I think. We have a committee of 8 students chosen from 25 students. Committees are good examples. That's a 25. Committees are a good example of a combination because the order that people are chosen in doesn't really matter. You just care that you're on the committee. So that's C of 25, 8 or 25C8. And crack the calculator for that one. 25 NCR, it's above the 8 button on my calculator. 8. And that is 1081575. So a little over 1 million, right? Different ways to choose 8 students from 25 students. Seems like a lot, but assuming I did that right, does seem like a lot. 25 NCR 8. Sure enough, right? Okay. So let's see. Or I was gonna do example 6 from the book. A bit is a 0 or 1. We do some of these coding examples on and off. So a bit is a 0 or a 1, right? It's a storage space in your computer that holds either a 0 or a 1. So a 6-bit string is a string of zeros, 6s, zeros, or 1s. So 0, 1, 0, 1, 1, 0, right? There's a 6-bit string, or 1, 1, 1, 1, 0, 1, right? This is a 6-bit string. And so how many, first of all, let's say how many 6-bit strings are there? Well, there's 2 options for each space. So this is going to be 2 to the 6th power. 2 to the 6th power is 64. There's 64 different 6-bit strings. On the other hand, how many strings have 3 zeros and 3 ones? Now, I don't have to say 3 zeros and 3 ones, because if I have 3 zeros, I have to have 3 ones, because otherwise it's a 6-bit string, right? Well, that's a combination, because you've got 6 different spaces, and you're choosing, out of those 6 different spaces, you're choosing 3 of them when you put the zeros, and 3 of them which you put the ones. I mean, it could be 0, 0, 0, 1, 1, 1, it could be 0, 1, 0, 1, 0, 1, it could be 0, 1, 0, 0, 1, 1. I don't know, I'm losing count, but okay, how many are there? Well, there's C of 6 spaces to choose from. You're going to put the zeros in 3 of them, and as a rule of thumb means multiply, right? And once you've done that, right, this is actually a conditional probability. Well, it's not a probability, but it's a conditional multiplication principle. Once you've done that, you have 3 slots left, and you're going to put 3 ones into those. The book doesn't spend a lot of time writing down things like combination 3 choose 3, because that's just 1. But I want you to think about, if you've got to put 2 things in, I want you to think about these and these, right? And we're going to talk more about this concept in a little bit, right? But that's C of 6, 3. So 6 NCR 3, and that's 20. times 1, which is 20. So 6 different strings, 6 out of 64 have 3 1s and 3 zeros in them. How many have only 1 0? Right? 1 0. So how many have 1 0? That means your zero is here, or here, or here, or here, or here, or here. There's 6 different places for that. So you're going to choose a place for the zeros. You've got 6 comma 1 times what's left for the 1s. You got 5 spaces left for the 1s, and you're going to put 5 1s in there. And this is just 6. Just like I said, there's 6 different places for you to put that 0. So there's 6 different strings with 1 0 in them. I guess I used the setup from example 6, but I did not probably ask exactly the same questions. So, oh yeah, one more thing I wanted to do there. What's the probability? Oops. What's the probability that a string has 3 zeros? Well, the denominator is the total number of ways to arrange our strings, and that's 64. And the numerator is how many of those strings have 3 zeros in them, and that's 20 right there. So if the question says how many, of course you're looking for a whole number. But if the question says what's the probability, then you need to think about, well, I need a denominator and a numerator now, and they're done separately often. The numerator used combinations, the denominator used the multiplication principle, right? So you really, this is one reason these are challenging problems from this section, because you got to use a lot of the tools, right? You have to understand probability, you have to understand the multiplication principle, and you have to understand combinations. And so the fact that we're drawing all these things together makes these extra challenging problems. Let's see if I got maybe one more in me. Yeah, I did want to do this. So I'm going to look at example 7 in the book. And this is similar to this last one in that there's 2 different groups, right? So we're going to form a committee with 2 faculty members and 3 students. And committee means that's probably a combination, right? And we have 6 faculty to choose from. And I believe that it's 10 students. So this is going to be a little different than the bit strings that we just did, because when we did the bit strings, things disappeared, right? When we chose the 3 zeros, we only have 3 spots left for the 1s, but that's not happening in this case because these are totally different sets. You've got 2 faculty to choose out of 6, and you've got 3 students to choose out of 10, right? So this is going to be C of 6 comma 2 for the faculty, and times, right, C of 10 comma 3. And that final answer is 1,800. Because I dropped my calculator, I cheated and looked it up in the book, right? 1,800. And this is a typical combination style question. So we're going to come back and we're going to look at some different examples from this section in the book, from 8.5 in the book, because there's a lot of different things going on here. Okay.